Somewhere above you, right now, a point of light is spinning. 1,000 times a second, it is 11 miles wide. You could walk its circumference in an afternoon, and yet, it weighs more than everything alive. On Earth, multiplied by a number with 24 zeros, a teaspoon of it would outweigh a mountain range. A coin-sized piece would crush through the Earth's crust. Like it wasn't there. 3 months ago, this thing was a star 40 times larger than our sun. Then, in less than a second, it wasn't. What does it take to turn a star into something this small, this dense, this wrong? Every star is a war. Gravity pulling inward, forever trying to collapse the star into a single point. Fusion pushing outward, forever trying to blow it apart. For millions of years, fusion wins. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes heavier elements still. But every fusion reaction produces less energy than the one before it. Eventually, the star starts fusing iron. And iron takes energy to fuse. It doesn't give it back. The war is over. Gravity wins. In under a quarter of a second, a core the size of Earth collapses down to the size of a city. The outer layers of the star, still falling inward, slam into that impossibly dense core and rebound outward at a fraction of the speed of light. This is a supernova. For a few weeks, this dying star will outshine its entire galaxy. But that brilliant explosion is not the main event. It's the funeral. What's left behind, quietly, in the dark, is the real story. A neutron star. And to understand what that word actually means, you have to forget everything you know about solid matter. Inside every atom, there's mostly empty space. The nucleus is tiny. The electrons orbit far away, relatively speaking. In a neutron star, that empty space is gone. Gravity crushed the electrons directly into the protons. Atoms stopped existing as atoms. What's left is a sea of neutrons, packed together so tightly that the entire star is essentially one giant atomic nucleus, 11 miles wide. A single sugar cube-sized piece of this material weighs about 1 billion tons. If you stood on its surface, gravity would be 200 billion times stronger than what you feel right now. You would not be crushed. You would be flattened into a layer of atoms before you even had time to register pain. And the surface itself is not soft. It's a crust of solid crystal, likely stronger than any material found anywhere else in the universe, floating on an ocean of superfluid neutrons underneath. Mountains exist on this crust, but because gravity is so extreme, a mountain here is not what you're picturing. A neutron star mountain is considered tall if it's the height of a coin. Anything taller collapses instantly under its own weight. And this thing is not still, it's spinning. Some neutron stars, called pulsars, rotate hundreds of times every second. Picture something heavier than the sun, spinning faster than a kitchen blender. Along its magnetic poles, it fires twin beams of radiation out into the galaxy, sweeping across space like a cosmic lighthouse. From Earth, we don't see a star. We hear a heartbeat, a radio pulse arriving with the precision of an atomic clock. The first time astronomers detected one of these signals, in 1967, some genuinely wondered if it was a message. They nicknamed the signal LGM-1, Little Green Men. It wasn't aliens, it was something almost stranger. A dead star, still ticking, long after everything else about it had stopped. So here is the real answer to the question. We started with, how does a star 40 times the size of our sun end up smaller than a city? It doesn't lose its mass, it loses its space. Almost everything that made it a star, the volume, the distance between particles, gets crushed out of existence in a fraction of a second. What's left is not a smaller star, it's a different kind of object entirely. Matter behaving by rules that don't apply anywhere else in the universe we can reach. And this isn't even the final stop. Add a little more mass to that neutron star, cross one more invisible line, and space itself stops being able to hold it together at all. What comes after a neutron star collapses even further is not a smaller city, it's not a smaller anything. It's the edge of a black hole, and that's where we go next.